So our core, or where we're going to start our analysis from, is the following circuits. So we can see this represented with a PNP BJT in this way, where we have some collector resistance RC between the collector of our transistor and VCC. We are going to take our output voltage at the collector, and unlike our common emitter amplifiers, we are going to apply a DC bias voltage VB at the base, and we are going to apply our input here at the emitter. Okay. So any amplifier in which we apply our input signal at the emitter and take our output signal at the collector constitutes a common base amplifier. We can represent effectively this exact same circuit using PMOS transistors like so. Here's the in, here's the out, here's VB. And I did not mention this previously, it slipped my mind, so I apologize. The small signal model for a PMOS, or excuse me, not a PMOS transistor, a PNP transistor is literally identical to the small signal model for an NPN transistor. You don't have to change any signs, any directions, or literally anything. The exact same small signal model works for both. Okay. All right, so let's draw our small signal model for this guy. Arbitrarily choosing the NMOS, although it's the NPN, although again, it really actually doesn't matter at all. So our small signal model, if this is our base terminal, here is our resistor R pi and our voltage VBE. Down here is our emitter terminal. Here is our collector. And for now, we're going to ignore the early effect. So since our power supply VCC looks like an AC ground in our small signal model, between the collector and ground, we have our resistance RC. Okay. So I'm going to put that guy over here. And this node down here at the bottom is going to be our ground. Our base terminal is also connected. Donald, you got a question? So this is VBE, GM-VBE, R pi, base, collector, emitter. This resistor right here is going to be RC as soon as I remember to write that part down. So since our base terminal is connected to a DC voltage and we turn our DC voltages off in our small signal model, that means our base terminal is effectively just shorted to ground in our small signal model, like so. And lastly, we have our input voltage, which is an AC voltage, so it needs to show up, and it is placed between the emitter and ground. So here is Vn. Excuse me. So this is what our small signal model looks like for our common base amplifier. Okay. So let's take this and analyze it to determine the input resistance, output resistance, and voltage gain, which is what we're going to do for literally every one of these over and over and over again. Okay. So I'm just going to make a copy of this. All right, so I'm going to call this current IN, okay, since we're going to determine our input resistance. And IN, using Kirchhoff's current law, is just a combination of this current flowing through the resistor R pi and this current flowing through our dependent source. Okay. So applying Kirchhoff's current law, we can see that IN is just negative VBE over R pi minus GM VBE. Everybody okay with that? That's the current flowing to the left and up through the resistor R pi, since it's flowing into the negative polarity terminal first. That's why we have a negative sign. Then our GMVBE term, we get a negative sign because the direction of current flow is opposite as to that is what is being supplied by our source. Okay. So what's the relationship between the quantity Vn and the quantity VBE in this circuit? Exactly right. So Vn is exactly equal to negative VBE. And from this, Rn, which is simply Vn over In, we get one over R pi plus GM. And that's it. Well, I think so. Hold on, sorry. Yeah, that's exactly it. Okay. Now, we can rewrite 1 over R pi as GM over beta. So GM over beta plus GM on, actually, this should be to the -1 power. Sorry, messing up my notes here. Which is approximately equal to just 1 over our transconductance. Sorry, and my algebra mixed up there. Okay. So 1 over R pi is equal to GM over beta. If we factor out the GM here, we're going to have GM multiplied by 1 plus 1 over beta. So for beta values that are large, somewhere in the order of several tens to, all the way up to 100 or so, the larger beta is, the more this looks like simply 1 over GM. So looking into this, the input of this transistor amplifier, we see a resistance that is the reciprocal of our transconductance. Now, I'm going to scroll up here. What if we're looking for our output resistance? What are the changes that we make when we're looking for our output resistance? We short the input. So that guy is a short circuit. And then we apply our test voltage to the output. The output resistance calculation for this circuit is literally the exact same thing as the output resistance calculation for our common emitter amplifier cord, right? So let me scroll up here real quick. The difference between a common emitter amplifier and the common base amplifier is that we're effectively swapping a DC voltage with the AC voltage, right? But when we're taking our output resistance measurement, we short the AC voltage that we're applying. So they look to be the exact same quantities, okay? Does that make sense to people? If not, it's okay. I'm happy to explain stuff. But we're going to do a lot of that. Well, it looks like this other thing that we've already analyzed. So let's not spend a whole hell of a lot of time analyzing, okay? So just to be clear, when we're determining our output quantity, this guy is ground. This guy is ground. And we're looking in here. If I drew, I'll just do this quickly over here, a common emitter amplifier, I would have VCC, RC, VN, VF, right? For our output resistance calculation, this guy is ground, this guy is ground. We're looking in here. What's the difference? There literally isn't one, okay? So what should our output resistance be then? Just RC, absolutely right. So R out is equal to RC, and I'm just going to put here same analysis as common emitter core, so that you can refer back to that analysis in your notes if you need to verify it for whatever reason. And then we're going to move along to our voltage gain. So for our voltage gain relationship, I need to actually label what V out is. The output voltage is taken at the collector terminal with respect to ground. So it's simply the voltage drop over the resistor RC. It should be fairly straightforward here that V out is equal to the resistor value RC times negative GM VBE, because the current GM VBE is flowing into the negative polarity terminal. As Mr. Boyle pointed out a moment ago, VBE is the exact same thing as VN, excuse me, negative VN, or actually that could have worked. Negative VB is equal to VN is how I'm going to choose to write it. And so if we take V out divided by VN, what we're left with is our voltage gain, AV, is equal to positive GMRC. So a common emitter amplifier gives us a gain of negative GMRC, and a common base amplifier gives us a gain of positive GMRC. RC. So we have effectively the exact same magnitude of the gain here, right? Just GMRC, whether or not we have an inverting amplifier or non-inverting amplifier, effectively just depends on whether we apply our input signal at the base or at the emitter. So these amplifiers seem like they behave fairly similarly, but they have vastly different input resistances, right? So for our common emitter amplifier, the input resistance was R pi. And for our common base amplifier, the input resistance is 1/GM, right? So that's really the thing that's going to tell us as to which one we want to use for a particular application. Do we need a relatively high input resistance or do we need a relatively low input resistance? If so, we use one versus the other. All right. So let's now mess things up by including the early resistance again. All right. So with the early resistance included, or the early effect included, our small signal model is going to look something like this. So here is our base. Here's our emitter terminal. In parallel with our current source, we're now going to have that resistance R naught. And then over here is our collector, right? The input voltage is still applied here between the emitter and ground. We still have our collector resistance RC over here on the right, over which we measure our output voltage. And then over here on the left, we have our short circuit to AC ground, that is the DC voltage, V capital V. All right. So this is our small signal model. Is our input resistance going to change? How did we look at the input resistance a couple of minutes ago, right? We simply applied Kirchhoff's current law at this node and then added all the currents together and got a relationship. Well, this resistor R naught is connected to that emitter node, so that means our input resistance is absolutely going to change. Okay. Let's see. So just save some. That's not what I wanted to do. Trying to just save myself some time redrawing this thing over and over again. All right. So for our input resistance relationship, again, let's call this current IN. We're going to have this guy, and this guy, right? I am going to redraw this circuit in an attempt to make our analysis here a little bit easier. Okay? So I'm going to redraw this circuit in a kind of a circuits one representation because I teach circuits one so much that that's how my brain processes circuit analysis. So that was slightly too far. So let's say that we have this guy, right? So I'll put my input voltage here on the left, and in parallel with that input voltage, I have my resistor R pi, and the positive polarity terminal of my input voltage is associated with the negative polarity terminal of my voltage VBE. So I'm going to start off looking like this. So effectively all I've done here is just swap these two guys, switched them around. This is my emitter terminal. And this guy down here is effectively my base terminal. All right. Now I have my current source. The current is flowing from the collector to the emitter. So we have GM VBE up here. We have R naught down here. This node is my collector terminal. There's where RC is. So between the collector and ground, or my base. So, let me draw IN real quick. So this guy still looks fairly gnarly, but I can simplify this representation by simply performing a source transformation on that current source in parallel with that resistor R naught. Okay. Everybody okay with that? So this is a dependent current source. The arrow is directed to the left, which means the positive polarity terminal is going to be on the left. And then the negative polarity terminal obviously will be on the right. And so what I'm going to do is I'm going to slide that voltage source down here. Okay. So what this is going to look like in my feeble-minded attempt to make sense of this thing in circuits one relationships. Here's the resistor R pi. Up here, I'm going to have R naught plus RC. And then here, I'm going to have GM VBE times R naught as my voltage. And again, my current IN. So it's now, in my opinion, a little bit easier to analyze this guy because we can effectively just treat that bottom node as a ground. So what I mean by that is if we apply Kirchhoff's current law, we are going to see that the quantity IN, I'm going to go back and forth because I ran out of space here, is equal to the current flowing down through the resistor R pi which in terms of Vn is just what? No, we're too far ahead, okay? I want the current flowing down in terms of that voltage. Vn over R pi, just good old Ohm's law. And then to that, I'm going to add the current flowing to the right through the series resistance of R naught plus RC. So that's going to look like Vn minus this guy over R naught plus RC, right? Now, as Mr. Boyle pointed out a moment ago, Vn is again just negative VBE. And so I can make a substitution there. And what I will find is that my input resistance, Vn over In, is the inverse of 1 over R pi plus 1 plus GM R naught over R naught plus RC, all to the negative 1 power. So effectively, it looks like R pi in parallel with this other conglomeration, right? That's a pretty significantly different look at our input resistance is what we saw with the early effect not included. Okay. Definitely doesn't simplify down to just simply 1 over GM anymore. All right. For our output resistance, what do you think we're going to have? The output resistance with the early effect included should look like the output resistance of a common emitter amplifier with the early effect included as well, right? So look at your notes from Friday. What do we see? Exactly right. I'm just going to put here same as CE core with early effect because it's literally the exact same analysis. For our voltage gain relationship, I want to look at this guy again real quick here. So we're trying to figure out the relationship between V in and V out, where this V out will just be the voltage drop over resistor RC and this circuit right here. So I'm going to use this simplified representation to determine my voltage gain relationship. Everybody okay with that? So let me take a snapshot of this guy. Come down here. I'm going to erase this ground thing up here. And let's call this plus minus V out, just so we're clear about what's going on. All right. So V out, as we've done in every single circuit that we've analyzed to this point, is going to be voltage drop over RC, which is simply the current flowing through the resistor RC multiplied by RC. Good old Ohm's law, right? So we could say that V out is equal to RC times this current, which flows into the negative polarity terminal, and also the current flowing through the resistor R naught. Right. So just to be clear here, I'm saying that we're going to take this current right here, which is a combination of this guy and this guy. So we're going to have GM times negative Vn, since we've established that Vn is equal to negative VBE. Plus V out minus Vn over R naught. Everybody okay with that? V out, Vn divided by R naught, just good old Ohm's law. So I notice actually right off the bat here that I've made an error in my notes, so I'm going to have to do algebra in front of you guys, which should be mildly terrifying, but I think we'll get through it. So if I distribute things here, this is going to look like GM RC Vn with a negative sign minus Vn times RC over R naught. And then I'm going to have plus V out RC over R naught. Right? Have I done my algebra here correctly? So this negative in front of this Vn is where this guy comes from. I'm just distributing my RC. I've split this guy up into two terms, right? So RC times negative Vn divided by R naught is where this guy comes from. RC times positive V out over R naught is where this guy comes from. We all okay? So moving things around a little bit, I'm going to have V out multiplied by 1 minus RC over R naught is equal to V in multiplied by, let's just call this negative V in to make the math a little easier. Negative V in GM RC plus RC over R naught. And so from this, our voltage gain of V out over V in is going to be negative GM RC plus RC over R naught divided by 1 minus RC over R naught. Now the question here is, did I screw up a sign somewhere? Because it seems odd to me, and should probably seem odd to a lot of you guys, that the voltage gain was positive when the early effect was ignored. Why would it be negative when the early effect is included? The short answer to that is not really sure. That's exactly what it is. Yes. So the negative sign goes there, negative sign goes there. Okay, so that literally just negative sign goes here. Takes care of that. And there we go. Thank you, Annabelle. Wonderfully astute observation. So what influence does the early effect have on the operation of this guy? Right? So if we look at our game here, this portion right here is what we started with without the inclusion of an early. Okay, so we're adding to that some quantity RC over R naught. Actually, let me double check the signs to make sure that this guy isn't supposed to have a positive sign now. Okay. Yeah, it should have. So sorry, just to be clear here, when I subtract this term on the right hand side here and I factor out a negative V naught, that's going to put a 1 plus in the bottom, like so. So our early effect here looks like it's increasing the voltage gain because we're adding some value to our original GMRC. But then we are dividing by a number that's greater than 1 as well. So we should see that overall this thing actually tends to decrease the gain a little bit, which is exactly what we saw in our common emitter amplifier. Okay. So anybody have any questions on this? And I apologize for the mistakes in my notes, which led to some awkwardness with the signs and all this kind of stuff. At some point, I just need to make PowerPoint slides of all this and not make you guys redraw this shit over and over and over again, but one day. All right, so what we're going to do now is we are going to put a degeneration resistor in this guy, just like we did for our common emitter amplifiers. Okay. So with emitter generation, here we have our resistor RC, taking our output voltage here. Here's VB. We're applying our input voltage here. So everything is effectively the same to this point. And then we put some resistance RE here. So let's talk about our input resistance measurement here. We're not even going to actually have to draw the small signal model for this part at all. Okay. So if I look up in this direction and I call this Rn prime, what do I see if we ignore early effects? What did we see when we did that analysis 12 minutes ago or whatever it was? So let's ignore RE entirely for right now. If we're looking in and up between this node and AC ground, that is VCC, what do we see? Look at the input resistance of the common base amplifier core. 1 over GM, right? So we see 1 over GM between this node and ground. Looking up, we see RE looking down. So RN is just those two in parallel because they're both connected between that node and AC ground. Does that make sense? Rn is Rn prime in parallel with Re, which is just 1 over Gm in parallel with Re. What about Rf? Should just be RC, right? So let's talk about why this doesn't affect anything. When we do our output measurement, our output resistance measurement, what does Vn do? It's shorted. So we have ground on this leg of Re, ground on this leg of Re, so it doesn't have any effect whatsoever on our output impedance. Sorry, just RC. All right. Let's look at our voltage gain. This one we're actually going to have to do arguably a little bit of analysis here. So let's draw our small signal model. Here's our base. Here's our resistor R pi, over which a voltage drop VBE occurs. Here's our emitter terminal. GM VBE. Here's our collector. This bottom node down here is effectively our AC ground. So between our collector and AC ground, we know that we have that resistor RC. Between our base and ground, we have a short circuit because that voltage VB was a DC voltage. Between the emitter and ground, we have our degeneration resistor RE. Here's our input voltage Vn. Here's our output voltage Vn. Anybody have any problems with this small signal model? All right, so what's the gain? What effect does RE have? So V out is the voltage drop over RC, negative polarity on bottom. Julia, what's the current that flows through that resistor RC? Yes. So I would argue that this current isn't the current flowing through RE. The current flowing through RE is just Vn over RE, right? This is the current that flows through RC. What's the relationship between VBE and Vn? Right, so our gain is still just positive GMRC. This degeneration resistor doesn't do anything to our voltage gain, right? So V out is negative GM VBE times RC. Vn is negative VBE. And from this, our voltage gain is positive GMRC. So this is a pretty huge result as compared to our common emitter relationship, right? For our common emitter amplifier, emitter degeneration caused a decrease in gain. For this guy, no change at all. Let's look at what happens when we include a base resistance. Generation. And base resistance, all right? So something along the lines of this. Here's RE. Here's RB. And this is VB. So in the last problem, or the last thing where we just had the emitter degeneration, we were able to look up and see our original common base core amplifier and then look down and see a resistor, okay? So the question that we should be asking ourselves here is, if we put a resistor between the base and ground, does that change what we see when we look up? Right? So let's look at our original circuit, back several pages at this point. If we have a resistor right here, does that change the value of this current IN in some way? Yeah. Absolutely, right. So we're going to have to go through the steps here and actually figure out what's what. So let's draw our small signal model, and I'm just going to draw it over here and then make copies of it as is needed. Here's R pi, VBE, GM, VBE, let's put our emitter resistor here. And here. Here's RC, over which our voltage drop V out occurs. Here is RB. So let's start. Are we all in accord that this is what our small signal model is supposed to look like? So let's circuits oneify this guy again to make our analysis a little easier here, right? So I'm going to start with my input voltage on the left-hand side. And in parallel with that directly, I have my resistor RE. Then in parallel, I'm going to have R pi in series with RB. And the negative polarity terminal of VBE is associated with the positive polarity terminal of VN. So that's going to look like negative VBE positive, like so. Here is GM VBE. Here is RC. Are we okay with my simplification here? All right. So we call this guy my current IN. IN is just going to be equal to this current plus this current plus that current using KCL. So that's going to look like VN over RE plus VN over R pi plus RB minus GM VBE. So we need to figure out how VBE relates to VN here. I would argue that that's a simple voltage division relationship. Anybody got a problem with that? All right. So if the potential difference between this point in the circuit and this point in the circuit is VN, and we're just looking for the voltage drop over one of these resistors, that means we are well qualified to use voltage division. So VBE is going to be negative VN times R pi over R pi plus RB, where the negative sign comes from the fact that we would expect voltage division to occur, positive polarity on top, negative polarity on bottom. Bailey, got a question? That's supposed to be RB, thank you. Thank you. So if we substitute that relation, what the hell is happening? If we substitute that relationship in here, we're going to get IN is equal to VN multiplied by 1 over RE plus 1 over R pi plus RB plus GM R pi over R pi plus RB. And since GM times R pi is equal to beta, write that up here. We can see Rn is simply 1 over Re plus beta plus 1 over R pi plus RB to the negative 1, right? So our base resistance changes that value that's looking up by a considerable amount, but we still effectively just see that bit in parallel with RE. Anybody have any questions here?
Beta plus 1.
Yes. If GM R pi is beta, and these have the same denominators, then I'm just lumping these two terms together. So yeah, that's just beta plus 1 over R pi plus RB. All right, output resistance. What do you think this is going to be? RC, absolutely right. And for our voltage gain, let's look at this guy right here, okay? So V out is this guy. So the current flowing through RC, let me draw the V out. So our output is just going to be negative GM VBE times RC. Everybody okay with that? Well, we know what VBE looks like, so we would just substitute that relationship in. Okay? So let me write this down. V out is negative GM VBE RC, or negative GM RC times negative VN R pi over R pi plus RB. Those negative signs cancel each other out. When we divide both sides by VN, our voltage gain becomes GMRC times a factor of R pi over R pi plus RB. And we can also write this as beta RC over R pi plus RB. Since GM times R pi is simply beta. Okay. Let's mess with things further. Now we put a source in there. Sure. Yes, beta times RC over R pi plus RB. Am I good to start on something else? All right. All right, so let's do common base with a source resistance. All right, so here's VCC, RC, V out, V in. Actually, I screwed that up because that's where, not source, collector. No, sorry. Okay, I'm confusing myself with the nomenclature here. Let me explain why my head is breaking right now. Okay. The reason why I said, oh, it can't be a source resistance is because this isn't a MOSFET, so there is no source terminal. what the resistor that I'm including here would represent is the resistance of whatever is generating our input signal, like if we were connecting a practical source to it. So I'm going to call it signal resistance and call this guy R sig so I stop confusing myself. Here's VN. All right. So if I look in here at the node just past the signal resistance, what do I see?
Just past it, it'll be the exact same, it'll be 1 over 2.
Right, 1 over GM. So from this node to AC ground, I see 1 over GM, and this is in series with that. Everybody okay? So our input resistance, Rn, is just R sig plus 1 over GM. What's the output resistance going to be? RC. So let's talk about our voltage gain here. All right. So from this node, let's call it VE for the emitter. We have a pretty straightforward relationship between VE and V out, right? Because that's just the gain of our common base core amplifier. So we can say that V out over VE is GMRC. So now we need to come up with a relationship that gives us VE over VN. Any thoughts? This is pretty similar to what we did towards the end of the lecture on Friday. Okay. So from the perspective of our input signal, it sees this resistor R sig and then a resistance 1 over GM. Okay. We are trying to find a relationship between the input resistance at this node and effectively an output, or excuse me, the input signal at this node and effectively an output signal at this node. So what we have in essence is VN R sig 1 over GM. And then that voltage VE, excuse me. So how are we going to get this relationship? It's just a voltage divider, exactly right. So that's just going to look like GM to the -1 over R sig plus GM to the -1. Our voltage gain is then just these two quantities multiplied by each other, because we're just breaking this down into a two-stage amplifier, right? So I'm going to have GM RC multiplied by 1 over GM times 1 over GM plus 1 over R sig is going to look like RC divided by R sig plus GM to the -1. All right, we only have one last thing to do on this, but we are running out of time, so let's finish up common base amplifier. Actually, I take that back. It looks like I have two different circuits. Okay, well, we're going to finish up common base amplifiers on Wednesday. Okay,